Okay, so hello everyone and welcome to SciCam, which is normally an online magazine-style science show, but because it's a science festival here in Cambridge, we're doing a live recording of the show which will get put on YouTube later. We've got me, myself, and three other members of the university who have each got different topics to talk to you about, and after everyone's spoken you'll have a chance individually to ask questions to all of the speakers today. So I'm going to get started, and you may have all noticed that you had an elastic band on your seat as you came in. And what I'm talking about is how the elastic band can actually tell us something about a fundamental law of the universe. So to do this, I'd like you to all start off by picking up your elastic band. Don't flick at anyone, please. I'll get in trouble. Don't eat it. Anything stupid. Health and safety, very important. What I'd like you to do is just hold it up to your, always like a moustache, just right up to your skin there, and then I'd like you to pull it sharp, and then I'd like you to let it go, and just do that a few times and just see what you feel as you pull it. So, anyone, what do you feel when you tighten it?
It's a bit warmer.
It gets warmer. And when you let go? Cooler. And so the reason it does this is kind of to do with how elastic bands work. Because elastic bands have got lots of really long molecules in it. And when the elastic band is loose and floppy like this, all these molecules are really twisted and tangled up in lots of different ways, so they're actually just taking up not very much space. Whereas when you pull it tight, you're forcing all of these molecules to basically all line up and all be straight rather than tangled before. And when you do that, you're decreasing what we call the entropy inside the elastic band. Entropy is kind of disorder, is a good way of thinking about it. When I said at the start there are lots of different ways they could be wiggling for the elastic band when it's at rest, that means they've got high entropy because there are lots of different ways that you could get the same outcome. Whereas when they're stretched out, there are very few ways that you can actually get it like that. So that's low entropy. And the fundamental rule of the universe says that entropy always increases. And so if when we're stretching it out, we're reducing the entropy of how the molecules inside the band are arranged, we've got to increase the entropy somewhere else. And that's, we increase the entropy involved in their motion. So they all start jiggling about a lot more. And that, in fact, is heat. And that's the heat that you feel when you're pulling it tighter. And then when you relax it, obviously, you had to put in some energy in. You can put in some energy and made it hot when you had it before. But when it relaxes, it's got to pull itself back in. It's got to do some work, and that work comes from the heat energy. So all the heat energy is used to pull it back in, and it gets cooler again. And in fact, this is more or less the opposite of what happens inside your refrigerator or your freezer. Because instead of having elastic bands in there, we've got a refrigerant, which is kind of held in temperatures and pressures, so that sometimes it's a liquid and sometimes it's a gas. But all the way around, we're always making sure that we're getting an increase in entropy, and that is, we set it in a way that will cool your fridge. We've got one equation. It's the only equation I believe we're having all show, and it's quite a simple one. So I think we can get away with it. And this says that ds, which is basically the change in entropy of a system when you heat it, is equal to dq, which is the amount of heat you put in, divided by its temperature. So if you put the same amount of heat into a really hot system, say outside your fridge, its entropy will only go up by a little bit. Whereas if you put it into something cooler, say inside your fridge, then the entropy will go up more. But when you're taking heat out of your fridge and trying to put it outside your fridge, you're going from cold to hot. So normally that would actually decrease the entropy overall. You'd end up with less disorder in the universe, and that doesn't happen. So in order to do that, what you have to do is you have to put in a lot of extra energy inside it so that it can really heat up the outside of the fridge as well. So you'll end up with an increase in entropy. And that's why fridges need electricity at all. Because so you can actually move heat from the fridge, which is cold, outside into the world, which is hot. And every step inside the fridge, you're increasing entropy. You start off with a liquid refrigerant, which goes into your fridge, and then the air inside the fridge, even though it's cold, it still has plenty of heat energy. And that gives some heat energy to your refrigerant and boils it. When something is boiled, all the gas molecules are free to move about, which means they're more disordered, which means they have more entropy. And then that current is going around and it gets to a compressor, which compresses all of this gas and makes it and turns it back into a liquid again. But when you're compressing it, obviously you're making it into a smaller space, so that's less disordered. But it heats up as well at the same time, so it gets more disordered overall. And then it's going to the back of your fridge, and it's now really hot. So it's hotter than the outside of your fridge, and so it can give all the heat away there too. And then the final step, it's allowed to expand and take up more space, more disordered. Every single step is doing the same thing, becoming more disordered. And some people get really confused about this whole rule, because some people go, oh, well, if things have got to get more disordered all the time, evolution's clearly nonsense, because that implies you started off with this whole mass of chemicals and it turned to us, and we're quite ordered. You might not think so when you see the state of my bedroom sometimes, but it is true. But the crucial thing is, we say entropy always increases in an isolated system. The universe is an isolated system because there's nothing else, there's no outside of it. A person is not. And so we become more ordered by making the world more disordered, and eventually in the future the world becomes so disordered that we've just got lots of, basically the temperature is just smeared out and becomes the whole universe, and it will just end up with a cold, dead universe. But we don't have to worry about that for a while. And finally, one last thing. It's a very strange thing that entropy always increases, because most laws in physics have what we call symmetry to them, in that you can like flip things around and run time backwards. Then everything kind of works the same way. But entropy doesn't seem to work like that. It always seems to increase going in one direction, and that's really weird. And lots of people argue about what this means in terms of physics and philosophy. But there's one other place where there's a really obvious breaking of symmetry in physics. And it's we kind of think that in the Big Bang, lots of matter and lots of antimatter was created. And because whenever we create matter and antimatter today, we create equal amounts of both. But when matter and antimatter meet, they annihilate and you just get energy again. So if we created the same amount, and whenever we destroy any, we destroy equal amounts of both, why is there any matter left at all? And we're just getting some slight ideas that antimatter might be slightly different and just might not stick around as long as matter. But that's active research going on now, and so we don't really know. All the results that we have so far is we might be onto something, but it's not enough. It doesn't explain how the universe can actually exist. Thank you very much.